the video I posted you was about the notations I was going to use in the class for translation as well as rotations. You can combine them with the vector formula I gave, but then there's a better way of writing those equations using what I described as homogeneous matrices. And if that was sort of vague, I think this will make it more clear, because this is actually applying what we did to derive equations for the forward kinematics of the manipulator. So what is a manipulator? Anything which is probably going to go and manipulate an object is a manipulator. So your hands are a manipulator. And when you have a manipulator, what you're interested in is being able to grip an object, maybe with the end effector, which is basically your hand. Okay, so when you place your joints in a specific configuration, that leads to a specific position and orientation for the end effector or the hand, and that's what we're interested in. So first step is to describe what is known as the forward kinematics. Given all the joint angles, describe the position of the end effector, or in this case, in our case, it could be the hand. So forward kinematics is given the joint angles, determine the position of, let's put position and orientation of the end effector, which is a fancy way of saying basically your hand. Okay, why we need it? Because we want to use the hand eventually to grip. So what we'll do here is, this exercise is about using the homogeneous matrices we talked about last class, and then eventually get to the point where we can animate the manipulator. So there'll be code which will show that the manipulator can be simulated, animated in Python. And then once we have that, then we can do more interesting things like, can you get the hand to draw, which will come to the later part of today's or maybe next class. Okay, so I'm going to draw, I'll start off with a really simple 2D example of a two-link manipulator. Okay, that's a pin joint. So all that joint does, it basically enables that link to rotate. And let's have this angle as θ1. Okay, and then we'll add another manipulator to make it more interesting. So this is our second link. And perhaps here there is the end effector. Okay, this is the gripper which is going to grip the object. Okay, let's give these points some names. So let's call this, let's say O, P, and Q. And clearly, if you want to draw the manipulator in Python, we need the positions of O, position of P, position of Q as those angles change. I forgot to draw the other one. So the other one is θ2. So when θ1, θ2 changes, P and Q keep moving, and we want to describe that motion of P and Q as those angles change. So we need location of point P, location of point Q as θ1, θ2 changes. And in that process, once we get those positions, we can just use our something simple as a line to basically join points OP and PQ. And that's what we'll do a little bit later. Now, what I'll do is, in order to use the homogeneous matrix, I need to define frames. Okay, so always you want to put a space frame. Let's call that OO, XO, YO. This frame is fixed to the world. It will not rotate or translate. Now, for each link, each angle, theta 1, theta 2 will have a frame associated with it. And what you'll see is that as that angle, theta 1, theta 2 changes, those frames will move. So here is X1, Y1, and this point, the origin here is O1. So that's the origin of frame 1. So now you see that when theta 1 increases, you see that X1 actually rotates with it. And of course, Y1 will also rotate, but X0, Y0 will not rotate. So X1, Y1 is a rotating frame. And that's what I meant last time when I talked about rotating frames. So we'll also put a frame right here. This is X2, Y2, and this is O2. Okay, so again, you'll see that frame 2 is actually not at O, but it is translated and rotated. And of course, it's going to change as theta 2 and theta 1 changes. Okay, so we want to figure out compute position of P and Q as a function of theta 1, theta 2, and I also need to give some length, otherwise you will not be able to compute those. So let's say that this length is L1, just to avoid, it's basically the distance between O and P. I'll not draw an arrow because it'll just clutter the whole picture. So L1, L2. So we need to describe the position of P and Q as a function of L1, L2. Okay, now you may say that's kind of simple. You don't need to do homogeneous matrices. You can actually use trigonometry. Okay, so one method is to use trig. Okay, and I'll just write it down in just one shot. It's not very hard to see that what I'm going to write here. So if you want the position of P, okay, and I want this in frame 0, then just by using trigonometry, you can see that it is L1 cosine theta 1, L1 sine theta 1. So remember, it's a vector because there's an x and y coordinate for point P. So you're just resolving along x and y axis. So similarly for Q, in frame 0, it will be L1 cosine theta 1, L1 sine theta 1. This gives you the position of P, but then you need to add to it the additional distance due to L2. So that will be plus L2. And now what I need to do here is I also would need this angle, which is the angle made with the x-axis or x0 axis. So it's going to be theta 1 plus theta 2. So we'll have L2 cosine theta 1 plus theta 2 plus L2. Yeah, and that's clearly the answer to position of point P and Q as a function of thetas and lengths. Okay, so that's fine. You can do this for this problem because you could visualize. But what we are after is, if we're given some complicated geometry where we want the position of some random point on the object, we just want to sort of create for formalic way or algorithmic way of figuring that out, so that we really don't need to draw a figure and visualize. We'll just have the equations and they'll automatically generate the position of the end effector. So some point of time in this course, we'll get into the symbolic toolbox, which will basically write symbolic equations instead of writing numeric equations. So we'll be able to derive all these things using a computer, not by using hand calculations. But before that, let's just try to use the method I talked about, homogeneous matrices. So this will be a method too. So let me copy this figure. I'll need it. Okay, so remember the formula I wrote earlier was the position. Let's call it something else. R0 is the homogeneous matrix from frame 1, or rather, let me do it this way. I minus 1, I. Let me check that. I shouldn't use R because that's used for rotations. Just use P. This should be I, my bad. This should be I minus 1. Now it looks good. Yes, so if I want to compute the position of P in frame 0, because I want it in frame 0 because that's how that's how I want to always visualize in the frame which is fixed to the world. Then I can write this as H10 P1. And then if I want Q0, what I need to do is, since Q, which is here, is related to frame 0 through the frame 1, I need to use two of those transformations. It will be H10, H21, Q2, because Q is technically attached to frame 2. Okay, so what I'm after is these two things. I need to be able to compute H and P. What is H? H is R001, I minus 1, I minus 1. So remember, this is a 3 cross 3 matrix. Okay, so what remains is the details of those various things. Let's fill those details and we'll have the formula for P and Q. Okay, so P1 is going to be the position of point P in frame 1. Okay, so the frame is not 0, but frame 1. So you can see that the position of P what's the position of P in frame 1? So what's its coordinate along x-axis? It's simply L1, right? Because L1 is along x1. What's its coordinate along the y1 axis? 0. And then I need to put this 1, which is just a placeholder to make the homogeneous matrix work. So you always have a 1 in the third row. Let's do Q. Okay, Q2 is the position of Q in frame 2. Okay, so what's the position of point Q, this is the point Q in frame 2? It's simply along x2 is L2. Along y2, it's 0. And 1 for just a placeholder. Okay, so we got P1 and Q2. Now we need to figure out what H10 is. That is R10. I'm just going by this formula. O1, 0, 0, and 1. Okay, R1 with respect to 0. This is a formula which I derive. It's you just need to know what angle corresponds to frame 1. It's theta 1. So cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1. And then these are the two zeros. This zero is basically these two zeros. Okay, and then we need the position of O1 in frame 0. Okay, since those points are pretty much on top of each other, there's no translation between O1 in frame 1 and 0. So it's going to be 0, 0, and then this 1 will show up here. Okay, so you can think of it this way, where this is R, the top left is R, and then 0, 0 for O1, 0, and then the ones. Okay, similarly, we can write H21 will be R21, O21, 0, 1. Okay, so for R21, it's basically the angle between frame 2 and frame 1. That's going to be theta 2. So cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2 0, 0. And now we need the position of O2 in frame 1. Okay, so let's see what that is. This is O2 in frame 1. So this is frame 1. So O2 is basically the same as P. So we're asking what's the position of P in frame 1. We found what the position of P in frame 1 is. So the x coordinate of P, that is along x1 axis, is going to be L1, right? And y coordinate is going to be 0. So just have to write L1, 0, 1. Okay, so what needs to be done is, all you need to do now is sub in the value for H10, which is over here, sub in the value for H21, which is here, P1 is here, and then Q2 is here. Okay, so I'll not do that here, but it's basically a matrix multiplication, a 3 by 3 times 3 by 3. When you do the multiplication, you get the following. P in frame 0, which is H10 P1, comes out to be L1 cosine theta 1 L1 sine theta 1, and then the 1. The 1 comes because, remember that it was a placeholder 1, which is used to keep to make this multiplication work. H10 H21 Q2. So when you do this multiplication, you'll get plus L2 cosine theta 1 plus theta 2 and then the 1. Okay, but essentially we got the same thing as what we got with trig. And the good thing is that this can be automated to the extent that if you know positions of Q and P locally, then you can figure out the coordinates in global frame 0 by just using those formulas. Okay, so with that, we're ready to start animating the manipulator. All we need to do is locate the position of 0, P, and Q, but we know the position of 0, P, and or OP0 and Q0 with that formula, all we do is put that in Python and just draw lines between the two, and we'll have the manipulator. And then if you want to see how the manipulator moves as theta1, theta2 changes, that can be done too. Okay, so this is this code which I wrote down. I'll obviously post it so you can then run it yourself. Essentially, this is taking what we did from the class on Python basics. Essentially, it's not some few lines of code, it's like 50 lines, but really setting up the parameters. I always want lengths to be 1 and 1. I set some theta1. I'm using a different package for math operations called import math. Okay, and then it is used in this fashion. So I wanted the value of pi, and I could use numpy, but I could also use math. Okay, as I said, sines and cosines not available. You either need to use numpy, or in this case, I've used math. What I've done here is define h01, h12. The same thing I wrote down here. You can see that they are basically a 3 by 3 matrix. To get h02, it's a multiplication of h1, h2. This is h1, h01 is h01, except this would be 02. Okay, the origin is 0, 0. I want the position of point P, so I actually do the same calculation. Instead of trying to given the final form, I just actually do the calculation here using those formulas. That's P1, that's Q2, and then I get Q0, which I multiplied 0.2 times Q2. And then it's just a matter of drawing a line between the 2 points. So origin to end of link 1, that's point P, and then point P to point Q. I do a few things like setting the axis limits, and then I tell it to pause for 5 seconds before it closes. So if you run this, theta1 is 0.5, theta2 is, I think it's 90 degrees. So you saw that the red was 90 degrees to the blue. Right? This angle is 90 degrees. You could also change this. So it's 90 degrees the other way. As a precursor to inverse kinematics. So inverse kinematics is the problem of, given in that context of the previous example, given Q0, compute theta1, theta2. So Q0, remember, is the end effector position. And you need to find what the angles are. Instead, it's a harder problem, right? How do you know what the angles are going to be is not trivial. So let's do root finding first, because that will be used extensively to do the inverse kinematics. So what I mean by root finding is, if you're given a function, let's say f of x equals x squared minus x minus 2, you're told to find the roots of this function. So f of x equals 0. So if, write it this way, if f of x equals 0, compute x. Okay, now you probably know that a quadratic equation could have what? 1 root, 2 roots, or no roots, right? So the best way to figure that out is probably to draw the function f of x as a function of x. So this is a parabolic equation, so it'll look something like this. Okay, and turns out that the roots are, well, one way of checking the roots is you make a guess, you put it in the equation and see if it comes out to be 0. So in this case, if I put -1, I think -1 will work. So maybe I need to draw this axis this way. Right? What's the other root? 2 is the other root, I think. 2. Okay, so simplest way is to draw a graph. Now that's possible in in 1 dimension, maybe also in 2 dimensions, but once you go to 3, 4, 5 dimensions, just becomes very hard to visualize and get the root, right? So what we'll do is that we will use a function in Python, which will be able to give us the root. So the equivalent, I think it's called fsolve. Let me check. Yeah, it's called fsolve. So we will use compute the roots of f of x. Okay, so I'll show you the code, and then we just take this code and then go on with this code and do inverse kinematics for the manipulator. Okay, so here is a simple example. The same example, you want roots of x square minus x minus 2. Okay, this is how you write x square in Python. The function is f of x, which is func x here. All I do here is I use root equals fsolve func 3. This is the initial guess, so the 3 is the initial guess. So what I've done here is I first plotted the function, and then I use fsolve to find the root, and then I say print root, so the root will appear here. So if I run this, that's the plot, the same one I drew. You can see -1 and 2 is the roots, but then it also gave me the root, which is 2. Now, there are 2 roots, remember, but only gave 1 root. So fsolve is designed to give you a single root. If you want to find the other root, you sort of have to give a different initial guess. So in this case, 2 was close to 3, and that's why it gave 2 as the root. But if you try, let's try 0 and see what it gives. So it gave -1. So it gave the other root. So depending on where your initial guess is, it will give one or the other root. Okay, but this function will not know if the root exists or not. So if it doesn't exist, it will tell you no root found, but that doesn't mean that there's no root. It could be that there's no root, could be that your guess is too far away from the actual root, and so you need to sort of try different initial guesses in order for the function to give you the root. And if you try it for various values and it doesn't give you a root, then it may be that there's no root. Okay, now let's take this and go a step further and ask the question, how do we put the end effector in the position we care about? Okay, so inverse kinematics of a two-link manipulator. Yeah, it's the same two-link manipulator we talked about earlier. This P, this is Q. Okay, let's say that we want this point, which is the point Q, to be here. Okay, so we want it to be here, and clearly there is some way to do this. I'm just making up something. Okay, so clearly there is some different configuration angles. Theta 1, theta 2. Okay, so it becomes a bit hard to actually do this by hand. So we'll use root finder. But so here the IK problem is also known as IK. Compute theta 1, theta 2 such that the end effector in this case is Q. Is that X ref, Y ref. So what are the things which are given are X ref, Y ref. Ref means, in this case I use ref to mean reference. L1, L2, unknown is L1, L2, and this is, sorry, unknown is theta 1 and theta 2. So this is the IK problem. So let's think of this. How would you do this without resorting to numerics? We know the position of Q. It was L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And then there was a Y component. And I want to place them at X ref and Y ref. Read it this way. So the first row should be equal to X ref. The second row should be equal to Y ref. Okay, so this is given, and these are unknowns. So you can see that in order to compute theta 1, theta 2, you need to do a non-linear, or it's kind of non-linear because cosine theta, it's not easy to invert that. So what we will do is we will write our f of x, or f of, in this case, theta 1, theta 2 as L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 minus x ref. And the second line would be L1 sine theta 1 plus L2 and we need to find the roots of this. So 0, 0. So now instead of being one-dimensional, which the earlier equation was, this equation is two-dimensional. You have two unknowns and two things which need to be checked for zero crossing or roots, two roots. So we will basically use fsolve for this. Okay, so now what I've done here is, in any case, just like before, you need to use something which the function f of x, which is the forward kinematics. So that part which we've covered was called forward kinematics. So my function here is called forward kinematics. It essentially gives me the value of it basically returns three things: the origin, which I don't care about, P, the point P, which I don't care about here, and the point Q. Okay, the point Q is what is of interest to me. I need to find the position of point Q and want it to be at a certain location. The inverse kinematics module or function basically computes, it basically returns the difference between, in this case, X comes from forward kinematics. So you can see it's the position of point Q along the x-axis in global frame. Y is a position of Y is a position of the point Q in the y-axis, and then I just do this difference, which is basically what I really want, which is the roots of this particular equation. Okay, so those are the two functions I need: forward kinematics and inverse kinematics. And then once I have L1, L2, 1, 1, you can choose whatever you want them to be. So here I want the manipulator to be along the x-axis at 0.5 meters and not along the y-axis. So that's 0. And so using fsolve, I can get θ1 and θ2. And now I can go back and do what I did earlier. I did a plot for a specific joint angle. So I did that next to make a plot. So not only will you see it, so you can see it's at, let me give a longer pause. Let's give it a 10-second pause. Okay, so you can see it's at 0.5, 0. The red being this is being the end effector, and the angles are over here. Now you see that that's one way of doing it. You could do it this way, but you could also have a configuration the other way, and that's because of the way I initialize the solution. And if I initialize it slightly differently, I hope that it'll give me the other solution. So this is how I initialized it. But maybe if I initialize it with a negative value, yeah, I tried this, but let's see if it gives me a different solution. You give me the different solution. So there are two ways of reaching the same point. One is downwards, one is upwards. So you see that the initial guess determines that. Okay, now we can take this a step further. When you see a manipulator doing things like drawing, all you need to do here is tell the manipulator it needs to move its end effector at different points along whatever curve you wanted to trace. So what I did was I just took the same code, but I said, now I want you to place the end effector at different reference positions in order to trace a circle. So this code here, all it does is takes the same thing for one point and extends it to multiple points. So first I generate a circle and then make the manipulator draw the circle. So that's no problem because it just takes the initial solution and goes with that. Make it play it again. Okay, so that's how you do inverse kinematics. Your second homework, basically, you can actually do the second homework now that I showed you this. You will actually be doing, there are like multiple curves which are available, cardioid and so on. You'll choose a curve, you'll trace it. And I think you'll also do a 3-link manipulator, which is, I think, more interesting than a 2-link manipulator.